Hey everyone, I am Miss Hu, your physics teacher. In this video, we'll be going through total internal reflection, where we will cover what is total internal reflection, the conditions for total internal reflection, the equation relating refractive index and critical angle, as well as some examples of the applications of total internal reflection. So now, first of all, what is total internal reflection? Let's look at an example of how total internal reflection can be seen in daily life. So here we have someone pointing a laser pointer through a perspex tube. So you can see if it travels in a straight line like so, but when we turn it at an angle, instead of the light traveling out of the tube, you can see how the light appears to reflect inside the tube. Now, as we know, reflection is due to a mirror, but there's no mirror over here. So we see light reflecting, but it's completely within this material itself. Now this is total internal reflection, not reflection, because there's no mirror. Total internal reflection appears to be quite similar to reflection in terms of how the light ray reflects when it reaches the boundary, but it is not an extension of reflection. And we'll take a look at that in more detail in an upcoming slide. Here is another real-life example which I'm sure that you have at least seen once in your life. If you ever observe an aquarium that's full of water, you might find that you can see the reflection of the objects inside the aquarium exactly as if there is a mirror behind this edge. But you'll find that for aquariums, they're just transparent glass sides. Yet when we fill up with water, one side, when you look at it from a certain angle, appears to be like a mirror. So for example, for this fish, you can see the reflection of the fish on that side, as if there's a mirror. But if you were to drain the aquarium of water, there's no mirror, it's just a piece of glass. So yes, total internal reflection acts just like reflection, but without a mirror. Another example you might see also in water is from underwater, when you look upwards towards the surface. You'll see there's a reflection of the object you're looking at the surface of the water, as if the surface is acting like a mirror. So again, no mirror, you see a reflection. This is total internal reflection. So it's reflection within the material without a mirror. So now let's get into how total internal reflection actually occurs. On this slide, this blue color rectangle block here represents the glass block, and outside it's air. So we're going to start off first with our understanding of refraction. If you don't know what refraction is, or if you need a refresher, please watch my video on light refraction. For now, we're going to go straight into this topic. Now, if there was a light ray traveling from glass to air, how does the light ray travel when it's in air? Remember, this is from glass to air. Light travels more slowly in glass and faster in air. So yes, light will actually refract away from normal. Now, you may or may not have learned this in refraction, but you should know that every time light refracts, a portion of the light ray will reflect. That means that every time light changes speed because it's changing medium, while some of the light ray will refract by traveling into the next medium, some of it will reflect it back into the material itself. This phenomenon, where part of the light ray reflects back into the material, is known as internal reflection. So the term internal reflection comes from the concept where the light ray is reflecting, meaning it's obeying the law of reflection, and it's reflecting back into the same medium, hence the term internal. This is why you'll find that some material like glass have a slightly reflective surface. That means when you look at a piece of glass, you can still see your reflection, but it's very faint. And the reason why you can see that image is because of the internally reflected light ray. If you were to do an experiment to observe refraction, you'll find that the bigger the angle of refraction in air, the less light that gets refracted out, and the more light that is internally reflected in. You'll find that the light ray that undergoes internal reflection obeys the law of reflection, where the incident angle and reflected angle are equal. To further help you visualize the angles, remember that the angles are measured from the normal line to the light ray. So we'll find that because light is traveling more quickly in air, light refracts away from normal, the refracted angle is larger than the incident angle. If you had done this experiment, you would know that if we were to move the incident ray in such a way that the angle of incidence becomes greater, you'll find that the light ray will refract even further away from normal. That means as I increases, R also increases. If you keep increasing I, you'll come to a point where the light ray will end up traveling along the boundary between glass and air. That means that the angle between the refracted light ray and a normal line is 90 degrees. Now, because it's a very unique situation, the value of the incident angle at which this happens is known as the critical angle. So the symbol used to represent critical angle is normally C. So C is the critical angle, which is the value of the incident angle when the refracted angle is 90 degrees. Now, before we move on, let's just talk about the equation that relates the critical angle to the refractive index. As you should have learned about Snell's law in refraction, the refractive index can be calculated as sine I over sine R, where n is the refractive index. Now, this is the simplified formula for refractive index. The actual Snell's law equation of n1 sine theta 1 equals n2 sine theta 2 can also be used here, but because we're learning this at the basic level, let's learn about the simplified formula to make this easier for us to understand. So as we know, in this formula, I should be the incident angle, while R is the refracted angle. However, this simplified formula only works for the situation where light is traveling from air or vacuum to the medium. For example, in this case, from air to glass. But as we can see from this diagram here, this is traveling from glass to air. As you should have learned, whenever you use this formula, regardless of however the light is traveling, you always take the angle of I in the equation and only in the equation as the angle in air, while the angle of R must be the angle within the medium. That means that in this situation, it's actually the opposite. R is going to go on top while I goes at the bottom. Now, in terms of the name, we still have to follow this rule where we look at the source of the light ray. That means if the light is traveling from glass to air, then yes, this is the incident ray, this angle is the incident angle, this is the refracted ray, and this is the refracted angle. But when we are substituting the value inside the equation, and only when it comes to the equation, we take the angle of air on top, that means this goes on top, while the angle in the medium, that means this one, goes at the bottom. If you want to understand why, please watch my video about the refractive index values in my refraction lesson. For now, let's get to how the critical angle is applied within this equation. So based on this condition, like I said, we're going to take the angle of air on top. We can see that in this second diagram, the value of the angle in air is now 90 degrees. So we're going to write here, I'm just going to do a direct substitution, sine 90 degrees. For the angle in the medium now is equal to the critical angle, which we put as C. So we're going to put C here in the bottom part of the fraction. Now, use your calculator and find out how much sine 90 is. I'll wait. Yeah, it's 1, right? So that's how in the end we get this simplified formula of 1 over sine C. That means n, which is the refractive index, is equal to the inverse of the sine of the critical angle. So n equals 1 over sine C is another formula which you can use to calculate refractive index. So this formula relates the refractive index to the critical angle. Now we're going to look at the application of this equation in some of the upcoming slides, but for now, let's move on to the third diagram, because no, we're not done yet with this slide. So you can see from the second diagram over here that the refracted ray has already reached its maximum angle. There's no way the angle can be greater than 90 degrees, right? But if you look at the incident ray, there's still plenty of space for the angle to increase, which means that the incident angle can still go greater than the critical angle. So what happens here then? The refracted ray can't go any larger. So what you'll find is that the light ray will end up reflecting back into itself. That means there's no more refracted light ray. The light ray will now 100% follow the line of the internal reflection. And because this is also reflection, it follows the law of reflection where the incident angle is equal to the reflected angle. Because there's no more refracted light ray, the light ray will be completely reflecting back into the same material. This is known as total internal reflection. So the term internal reflection applies only to a portion of the light ray that has reflected back into the material, but there's still some refracted light ray. Total internal reflection is when the light ray completely and totally undergoes internal reflection. There's no light ray that refracts out into the next medium. So for this to happen, obviously, this doesn't happen all the time. It only happens at specific angles. And that's why the critical angle is an important value to note, because the critical angle is kind of like the standard to determine whether total internal reflection happens or not. So you can see in the first diagram here, this is a situation where the incident angle is less than the critical angle. Most of the light ray will end up refracting out into air. That means it just undergoes the typical normal refraction. However, if the incident angle is exactly equal to the critical angle, then the refracted light ray ends up following the boundary. That means that the refracted angle is 90 degrees. And yes, in both situations, some of the light ray undergoes internal reflection. However, if the incident angle is greater than the critical angle, then all the light rays are 100% internally reflected back into the material itself. And this phenomenon is known as total internal reflection. So now that you understand this, you must know the conditions for total internal reflection, because obviously total internal reflection doesn't happen all the time. It only happens in this situation. There are two conditions for total internal reflection, and the first one is one that we've already discussed, which is that the incident angle must be more than the critical angle. The second condition is that light must travel from a higher to lower optical density. That means in this case from glass to air. This is true for any kind of medium. That means it could also be from water to air, oil to air, even if it's not to air. Even if, say, for example, from glass to water, then total internal reflection can also happen. Why can't total internal reflection happen when light is traveling from lower to higher optical density? Well, think about it. If light were to travel from air to glass, the light rays will be basically traveling the opposite of these main orange lines. That means that when light travels from air to glass, it's going to refract towards normal because it's moving from faster to slower. For total internal reflection to occur, the refracted light ray must refract in such a way that the angle of refraction is greater than the incident angle, so that it can eventually reach 90 degrees for the refracted angle, but the incident angle still has not reached its maximum. So then when you increase the incident angle, then yes, that's where you can get the light ray to be totally internally reflected. But if light was traveling from air to glass, the refracted angle always ends up being smaller. So you end up finding that this angle becomes so big, you could eventually reach 90 degrees even you point a light ray this way. You might find a light ray will refract in here, but it can never reflect back into itself because it can never reach a point where the refracted angle is so big that the light ray ends up internally reflecting. So you can think of total internal reflection basically being the situation where the light ray refracts at an angle such that it's so big it's got nowhere else to go but to reflect back into the material itself. Hopefully that explanation makes sense to you. One thing that you must understand about total internal reflection is that it is an extension of the refraction concept. A lot of students think that total internal reflection is an extension of reflection. Now, it's not. Now, remember, light reflection is about reflection in general. Like you can see, yeah, there's some reflection going on here. But when we talk specifically about the phenomenon of light reflection, we're looking at how light can reflect off a surface like a mirror. Total internal reflection does not involve a mirror. In fact, you can see that the understanding of total internal reflection starts off first with the understanding of refraction. That's why I said total internal reflection is an extension of the concept of refraction. You'll find that basically before this can even happen, refraction is going to happen first. So when we talk about understanding the topics, you can think of refraction as the main topic and total internal reflection is a subtopic of refraction. So don't be misled by the name. Total internal reflection is called this because the behavior is similar to reflection, but it is an extension of refraction because of how the light ray travels from one medium to another. So now that we know about the conditions for total internal reflection, let's go look at this example. So here we have a diagram which shows the light ray traveling from air to glass, where the incident angle in air is 50 degrees. Question is, how would the majority of the light ray travel? Would it refract closer to normal at A? Would it refract further from normal at B? Would it travel along the boundary of air to glass at C? Or will it undergo total internal reflection at D? So you can see that this question looks as if it's somewhat related to total internal reflection, but it's not. It's pretty much a trick question because in this case, light is traveling from air to glass. Now, remember that there are two conditions for total internal reflection to occur. Ooh, balloons. The first condition is that the incident angle must be greater than the critical angle. So it looks like, yeah, it fulfills that condition. But the second condition is that light rays must travel from higher to lower optical density. So in this case though, it's traveling from air to glass, which is from lower to high optical density. When light travels from air to glass, it's going to refract towards normal. So there will be no total internal reflection. Therefore, the answer to this question is A. Now, let's look at what happens when light travels from glass to air. So now in this case, light is attempting to travel from glass to air, where the incident angle within glass is 30 degrees. So to check where the light ray will travel, again, let's look at the two conditions for total internal reflection. The first condition is that the incident angle must be greater than the critical angle. We're given a critical angle of glass at 42 degrees, but the incident angle here is only 30. It's less than, correct? So total internal reflection will not occur, even if the second condition is fulfilled, where light is traveling from high optical density to low optical density. So that means in this case, it will end up refracting. So when light travels from glass to air, or from higher to low optical density, it's going to refract away from normal. So therefore, the answer to this question is B, where we can see that the light ray for B is further away from the normal than the original incident ray. And now let's look at a situation where the angle is now much greater at 50 degrees. So let's check against the two conditions of total internal reflection. The incident angle of 50 degrees, as you can see, is greater than critical angle. So yes, the first condition is fulfilled. The incident angle is greater than the critical angle. Second condition, light ray needs to travel from a higher to lower optical density. And yes, every time I do this, Canva likes to give me balloons. There we go. So the second condition is also fulfilled, which means that the light ray will now be undergoing total internal reflection. So not only is the majority of the light ray traveling to D, actually all of the light rays traveling to D. Light is undergoing total internal reflection. It's 100% reflected back into the glass block itself. Now let's look at further examples of understanding how refractive index relates to the critical angle. So we have on this slide here a comparison between glass and diamond. The value of n here refers to the respective refractive index values of glass and diamond. So glass has a refractive index of 1.5 and diamond has a refractive index of 2.42. Now before we make the comparison between glass and diamond, let us first calculate the critical angles of glass and diamond respectively using these values of the refractive indices. We know the formula of refractive index is n equals 1 over sine c, where c is the critical angle. So I'm writing it at the corner here as our reference. So to calculate the value of the critical angle, you take that formula and substitute the values accordingly. So for glass, it's 1.5 equals to 1 over sine c. So from here, we get c is the inverse of sine of 1 over 1.5. You're going to get a value of 41.8 degrees, which we're going to round to 42 degrees. So now let's do this calculation for diamond. So 2.42 equals 1 over sine c. So c is the inverse of sine of 2.42, giving us a value of 24.4 degrees. Let's just round this to 24 degrees, two significant figures. So what do these calculations show us? You can see that the greater the refractive index value, the lower the critical angle. So why is this relevant? Because the critical angle determines how easy it is for total internal reflection to occur within that medium. Let's compare glass and diamond because essentially what this slide is about, right? Now, you know how they always say that, oh, glass glitters more because it has more to prove. Okay, maybe that's not really a saying. So say you take a piece of glass and you take a diamond and you cut them exactly the same. The shape may be exactly the same, but no, they're not going to behave the same. So diamonds, of course, appear to sparkle more compared to glass, even though glass may be cut exactly the same way. So that's how jewelers are able to see immediately, hey, this is just a piece of glass. Of course, if you're comparing precious stones where the refractive index values are much closer to one another, then you need to have special expertise to be able to tell the difference between the different precious stones. But if you're just talking about normal glass and diamond, I think it's pretty obvious. So the refractive index of 1.5 is a typical refractive index values of the glass blocks that we use in our physics labs. Obviously, if they're going to use glass as fake diamonds, they'll be using one where the refractive index is a lot closer to the diamond. But anyway, let's get to the comparison right now. So let's look at this arrow diagram first. So let's say this represents how the light ray is traveling from glass into air. So let me label that for clarity. So say that this is glass and this is air. Light is traveling from glass to air. Whereas this diagram here will be for diamond. So that means the light ray is trying to travel from diamond to air. So we have the light ray traveling to the boundary between these two media. Now what we're going to look at is to see how the light ray travels when you're traveling from glass to air. That means we want to observe, will total internal reflection happen or not? So for this, I'm going to use an angle value that is between these two values of the critical angle. Let's say we take a value of 30 degrees. So 30 degrees for the incident angle in glass and also 30 degrees for the angle of incidence in diamond. Let's start first with the light ray traveling from glass to air. So you can see that the incident angle of 30 degrees is less than the critical angle of glass, which is 42 degrees. So as per the example we saw earlier, even though one of the conditions is fulfilled, meaning light is traveling from a higher to lower optical density, the first condition is not. The incident angle is less than the critical angle, which means that total internal reflection will not occur. You'll find that the light ray will end up refracting away from normal. Yes, there will be some light ray that will internally reflect, but it's only a small portion. A majority of the light ray ends up refracting out into air. Now let's look at diamond. So the angle of incidence we have in this example is 30 degrees. And as you can see, 30 degrees is already greater than the critical angle of diamond, which is 24. First condition is already fulfilled. Second condition, light is traveling from higher to lower optical density, diamond to air. That means that in this case, light will not refract out into air. It will undergo total internal reflection. So what this comparison proves to us is that the higher the refractive index, the lower the critical angle, and therefore the easier it is for light to undergo total internal reflection. So the reason why total internal reflection can happen more easily is because if the critical angle is smaller, it's easier for the incident rays to achieve a value of angle that is greater than critical angle. For example, the critical angle of glass is 42. So anywhere between 0 to 42, the light ray will still refract back into air. It needs to be greater than 42 in order for total internal reflection to happen. Whereas for diamond, any value that's already greater than 24 would have the light ray undergo total internal reflection. So then why does that make diamond appear to be more sparkly? It's because when we look at a diamond, it appears to sparkle because it's actually reflecting light to our eyes. Diamond is not a light source, so it doesn't shine. You can't shine bright like a diamond. There's no light source like a light bulb. So how diamond gets its light in the first place is because it picks up light from another source, undergoes total internal reflection, it goes to our eyes and we see, ooh, sparkly. So why can't glass do the same? It's because of the critical angle. To give you another comparison here, we have two diamond shapes here, exactly the same, but let's see how light travels. So if, for example, we have a light ray that comes in through this phase, we'll have the angle in such a way that the angle of incidence is 0, so the light ray will travel straight through, and let's say it reaches this boundary. So now the thing is, as we know, the incident angle has to be greater than 42. So there's a possibility that the angle here is less than 42. So if that were to happen, then you'll find that the light ray will end up refracting out into air, like so. I'm just going to put a normal line here to help you visualize better how the angles are. So the normal line is normal to the boundary at where the arrow reaches the point on the boundary. So here we have the incident angle and the refracted angle. You can see that the refracted angle is larger than incident angle. So what I'm trying to show you here is that the light ray ends up refracting out of the glass cut into air. But if we have the same light ray enter the diamond, because it's so much easier for light to undergo total internal reflection, that means this light ray could undergo total internal reflection. So the light ray is going to end up reflecting back into the diamond itself. And then when it reaches this point here, it can undergo another total internal reflection. So if you were observing the diamond from this side, for the glass piece, the light ray has refracted on the other side. So it doesn't reach our eyes. Therefore, when we look at this facet, it looks black. There's no light. But if you were to look at the diamond, because the light ray can reach our eyes, this face would look sparkly. So that's why diamonds appear to be sparkling so much more compared to a piece of glass that's cut the exact same shape. So just to help you visualize the reflected angle bit, I'm just going to put a normal line here so you can see clearly that the incident angle and reflected angle are equal based on the normal line. So as you can see, incident angle and reflected angle, incident angle, reflected angle. Now let's look at an application that doesn't involve jewelry or expensive stones. Something more practical and closer to our hearts, optical fiber. So the optical fiber is basically a material that is used to transmit light from one end to another end. The optical fiber is extremely useful because it is now used in a lot of high-speed internet communications. So I'm sure, for example, right now, those of you who are watching this at home, you're using high-speed internet connection, which uses optical fiber for your internet. But besides internet, the optical fiber is also used in devices like the endoscope. So endoscope is a medical imaging device where they put a camera on one end, screen on another. So the end of the camera is then placed into the patient's body, either through the throat or through the anus, in order to be able to observe the inside of a patient's body without cutting them open. So for example, the medical professional wanted to see what's on the inside of the patient's stomach. They don't have to cut the patient open. They just put the endoscope through the patient's throat down to the stomach, and they can see what's on the inside of the stomach because the camera is in the stomach and it's connected to a screen that the medical professional can observe. So how the optical fiber works is it uses light rays to transmit data. If you'd like to know how light rays are able to transmit data, watch my video on electromagnetic waves. For now, you just need to know that light rays can be used as a carrier wave to carry data. The thing is though, optical fibers cannot remain straight. For example, the data cables which contain optical fiber for the high-speed internet, they're not completely straight. The wires have to be able to bend when they connect it within your house. Or even the endoscope, when it's placed into the patient's throat, obviously the fiber must be able to bend so that it can reach the patient's stomach. So if the fiber was to bend, wouldn't there be a possibility the light ray will be refracted out into air? So this is where our knowledge of total internal reflection can be very useful. So the optical fiber typically looks like this. There's an inner core where the light ray will be traveling on the inside, and of course the inner core must be protected. So we've got the cladding glass and a plastic jacket. So the inner core must have very high refractive index, or as some would say, very high optical density, so that the light ray will undergo total internal reflection easily, just like how light was able to totally internally reflect more easily in diamond than in glass. Because of its very high refractive index or very high optical density, the light ray tends to undergo total internal reflection, and there will be very little loss of data. And that's also why optical fibers can provide such high-speed internet communications. So I'm just going to add that note that the inner core must have high optical density or high refractive index so that total internal reflection can happen easily. So the cladding glass, because it's transparent, it's possible for it to have an optical density as well. It must have a much lower optical density compared to the inner core in order to make sure that the light can undergo total internal reflection. The plastic jacket is just to protect the cladding glass so that it doesn't get scratched or broken. So sometimes in an exam question, you might be given a diagram of an optical fiber and you're required to draw a ray of light in the fiber undergoing total internal reflection. Just going to show you how to draw that ray of light. You draw a ray of light starting from one end and make it go straight until it touches the boundary here. Now it's always good practice to draw an arrow to indicate that's the incident ray. That means we're showing where the light ray starts from and where it ends up at. Now you have to show that the light ray undergoes total internal reflection. And remember that it still obeys the law of reflection, where the incident angle is equal to the reflected angle. So at this point, where the light ray reaches the boundary, we can draw a normal line just to prove that the angles are equal. For a curved surface, you might be wondering, how do we draw the normal line? For curved surfaces, remember that the normal line is normal to the tangent at that curve. Now, you don't actually need to have this line, which I've just drawn. That's the tangent to the curve. You don't need this. I'm going to erase this in a moment, but I'm drawing this here in order to help you visualize where the normal line should be. The normal line is perpendicular to the tangent of the curve at the point where the light ray touches that boundary. I know it's quite a mouthful, but basically just think of it this way. Look at the point where your light ray has touched that boundary, tangent to that curve, draw a normal line. So we don't actually need the tangent line. I'm just going to delete it now because I don't want you to think that you have to draw it in your diagram. It's not required. You only need to draw that ray of light. Now, the reason why we have the normal line here is to help us get a more correct angle of reflection. So we want to have a light ray placed in such a way that the angle of incidence is equal to the angle of reflection. So if you ended up drawing something like this would already be wrong because you can see that the angles are not equal. So you'd want to make the angle larger until we get the angle of reflection to be equal to the angle of incidence. Now you might find that the light ray is not able to go all the way out to the other side. In fact, for the exam questions, normally they'd like to see at least 2 points of reflection. So it's okay, in fact it's encouraged for you to draw the light ray until it touches the boundary one more time and draw another total internal reflection occurring. So I'm going to reposition this a little bit more first because it doesn't look quite right. Yeah, I'm cheating here a little bit. Now again, we're going to have our normal line to that point. Just going to adjust the line a little bit. Because it's always a good idea to have the arrows drawn. I'm going to draw the arrow here. And then the second reflected ray. Like so. So this is how you can draw the ray of light undergoing total internal reflection in an optical fiber. Now let's take a look at some other optical devices that use total internal reflection. These optical devices tend to use glass prisms. So let's look at how light behaves when it travels through a prism. To make this easier to understand, let's assume that all the glass prisms we have in our examples have the same critical angle as the glass that we use in the laboratory, which in this case has a critical angle of 42 degrees. So on this slide, we are looking at a diagram of a prism, and this particular prism is a right angle prism with two 45-degree angles. Now the angle is very important, which we'll take a look at in an upcoming slide. For now, let's focus on this prism. Now let's say a light ray is coming into the prism from the left-hand side like this. What happens at this point? Will the light ray refract? Well, there will be no change in direction if the light ray comes in perpendicular to the boundary. And that's because the light ray is parallel to the normal line. So if the light ray is parallel to the normal line or perpendicular to the boundary, the incident angle is 0. And that's why the refracted angle is also 0. When the light ray enters the glass prism, at this point, there's no change in direction. The light ray will continue to travel in a straight path. Now what happens is the light ray will keep traveling until it reaches this point on the other side of the prism. As we can see now, the light ray is trying to exit the prism at an angle. How much is this angle? Well, to determine the angle, let's first draw the normal line. So remember, the normal line is a line that is perpendicular to the boundary at the point where the light ray has reached. To figure out the angle, it's actually all triangular math. So we can see that this prism is a right angle prism, which means that this little triangle here, at this point, because the refracted angle is 0, that means this angle here is 90 degrees. If this is 45, that means that this angle is also 45. Because the normal line is 90 degrees to the surface, bada bing bada boom, when you do your calculations, you'll find that the angle between the normal and this light ray is also 45. Now let's recall, we've just learned about total internal reflection, and there are two conditions. So the first condition is that the incident angle must be greater than the critical angle. And as you can see, if the critical angle is 42 degrees, then yes, the first condition is fulfilled. The incident angle here is 45 and is greater than 42. Secondly, the light ray needs to be traveling from a higher optical density to low optical density. And yes, again, this is so. It's traveling from glass to air. That means that at this point, this light ray is going to undergo total internal reflection. And because this incident angle is 45 degrees, that means that it will also reflect at an angle of 45 degrees. And 45 plus 45, you get a perfect 90-degree angle. So that's why you'll find the light ray appears to do a beautiful reflection at a 90-degree angle between these two light rays. The light ray will then continue to travel until it reaches this point, and what happens at the exit point here is exactly the same as what happens at the entrance point. The light ray is traveling parallel to the normal line or perpendicular to the boundary, which means that at this point, the incident angle is 0, therefore the refracted angle is also 0. So if you have a glass prism where the light ray is traveling this way, you'll find that the light ray will do a beautiful total internal reflection like this. So a common application of a glass prism used this way is in a periscope. So there are two types of periscopes. There's a mirror periscope and there's a prism periscope. In this lesson, we're going to focus on the prism periscope. If you'd like to know more about a mirror periscope, I'll put that in another video where we compare the mirror and prism periscope. For now, let's focus on the prism periscope. What is a periscope? A periscope is an optical device which allows us to see higher than our eye line. Typically, it's used in a submarine, so when the submarine is submerged underwater, the periscope allows the people in the submarine to see what's above the water surface. So it's a thing that you always see in movies or cartoons where there's something poking out above the surface of the water. So that's the periscope. For the periscope to work, you need to have two glass prisms arranged in this way. How does the periscope allow us to see above our eye level? So let's say we've got the light ray coming in from the left towards the top, and as we've already learned, when the light ray enters the prism at this point, it's going to travel in a straight line without any change in direction. Then when it reaches this point, it's going to undergo total internal reflection. Then when it exits, again it continues to travel in a straight line until it enters the other prism. And again, what happens here? Same thing. Incident angle is 0, therefore refracted angle is 0. The light ray continues to travel without a change in direction until it reaches this point. So what happens here is exactly the same as what happens over here. There will be total internal reflection, and that's how the light ray is able to reach the eye of the observer. Now, one thing that you must take note of is that the arrangement of the prisms in the periscope is also very important. The correct arrangement of the prisms in the periscope that allows us to observe the object correctly is exactly as what's seen on this slide, where the two angled sides are parallel to each other. Just to prove this to you, I'm going to show you a second ray path, and I've colored this in yellow to make it distinct from the first ray path. As you can see, the second ray path goes through the exact same behavior as the first ray path. So how does this prove that we're seeing the object correctly? Let's say we're observing a tree. So you can see that the orange ray comes from the top of the tree and the yellow ray comes from the bottom. And when it reaches our eyes, the orange ray is still on the top and the yellow ray is at the bottom, meaning that the image of the tree will appear upright to the observer. Now, is it possible for the prisms to be arranged in a periscope where the image will appear incorrectly? Yes, so as you can see, the prisms in this periscope have been arranged differently, where the two angled sides are no longer parallel to each other. So I've left this left and right side open because I don't want you to guess where the light ray is going to come from. I'm going to show it to you. So now let's observe how the light rays are going to behave when they travel through the prism. So again, let's have the light rays coming from the left hand side towards the top, and this time I'm going to have two parallel light rays so that we can see straight away whether the image will be upright or inverted. Inverted here meaning upside down. So when the light rays reach this surface, the light rays are going to undergo total internal reflection. So as you can see, the light rays will totally internally reflect. They'll travel through this edge and continue in a straight path, again entering the next prism at this edge, traveling at the straight path down to this angled surface. But when it reaches here, the light rays are not going to come out to the eyes. We know the light rays are going to undergo total internal reflection, which means they're going to be reflecting into the glass block itself. That means the light rays are going to go this way back to the left. So the light rays are not able to reach the eye of the observer on this side. So if you're going to look at the periscope from this side, you won't be able to see anything because there's no light rays reaching your eyes. It'll just look really dark in here. So in order to be able to observe the image, you'd have to place your eye on the other side of the periscope. But as you can see from the light rays, the orange rays on top, yellow rays at the bottom. But when it reaches our eyes, it's now the opposite way. The orange ray path is at the bottom while the yellow ray path is at the top. That means that if we were to be observing the same tree, this time the tree is going to appear upside down to our eye. So if you want to use a periscope this way, you still can, it's just that everything will look upside down. So that's why the arrangement of the prisms in the periscope do make a lot of difference in the way the image appears to our eye. Now let's take a look at another way the same prism can be used in a different optical device. Say now we place a prism this way. Again, this prism is identical to the earlier one. It's a right angle prism with two 45-degree angles. This prism has a critical angle of 42 degrees. Now this time, we have the light ray entering this way towards this edge. How does the light ray behave when it enters a prism? Provided that this light ray is entering perpendicular to the surface, the incident angle is 0 degrees, while the refracted angle is also 0 degrees. So that means that when it enters the glass prism, it's going to continue traveling in a straight line on the same path until it reaches this boundary. So here we've got the normal line at the point where the light ray has reached this boundary, and this normal line is 90 degrees to the boundary. So at this point you can see that the light ray is trying to travel from glass to air. Let's check the incident angle value. So again, triangular math. This is a right angle triangle, a 45-degree angle, 90 degrees, which means that this angle is also 45. Therefore, the incident angle will be 45 degrees. So light is trying to travel from glass to air, and the incident angle of 45 degrees is greater than 42 degrees. So what's going to happen here? That's right, total internal reflection. So it's going to reflect at the same angle of 45 degrees, and the light ray is going to travel like so. So again, 45 degrees and 45 degrees, you get this beautiful ray path where the angle between these two light rays is 90 degrees. The light ray is going to keep traveling until it reaches the other edge. And at this point, again, let's find out what the incident angle is. So here's our normal line, and you can see, again, we've got a triangle here, 45, 90 degrees. The incident angle is also 45 degrees. So once again, it's going to reflect at 45 degrees, and you'll find that the light ray path will travel like this. So it reflects when it gets to this edge. Incident angle and refracted angle are both 0. That's why the light ray continues to travel in a straight path. So you get this really interesting ray path when the light ray enters a prism this way. Emergent ray over here is parallel to the incident ray entering the prism. So what optical device would use the light rays this way? Binoculars. If you ever use binoculars, you should have noticed that the eyepiece where you place your eyes are not in line with the objective lens. The objective lens is the lens which you point towards the object. That's why it's called objective lens. So how are prisms used in the binoculars? So as you can see, the prisms are placed in such a way so that when the light ray enters through the objective lens, they get totally internally reflected in both prisms before the light ray reaches the eyepiece. And this happens on both sides. So the reason why we place the prisms this way is to shorten the distance in which the light ray needs to travel from the first lens, which is the objective lens, to the second lens, which is the eyepiece. Because as we know, binoculars are used to observe faraway objects, and normally the light rays, when they travel through the lenses, they need some space in order for the light rays to be able to refract and then in the end magnify the image that we're looking at. So the prisms are placed in such a way to shorten that distance which the light rays need to travel so that the binoculars can be really compact, as opposed to a telescope which tends to be much longer. Now these beautiful ray paths that we see in the prism, periscope and the binoculars only work because the prisms that we are using are 45-degree prisms. So because of the 45-degree angles, the incident angle becomes 45, therefore the refracted angle is 45, hence giving us a total angle of 90 degrees. That's why the light rays will come out perpendicular to each other, like so. We're going to take a look at some prisms with different angles, but before we go into that, remember that just because the prism has a 45-degree angle doesn't mean you're guaranteed to get light ray paths that are perpendicular to each other. You must check the angle in which the light ray enters the prism. So for example, in this situation, if you have a light ray coming in from the left like so, do not assume that the light ray is going to continue traveling in a straight path like this. This is wrong. Why? Because at this point, the incident angle is not 0 degrees. See, what happens is, at this point, if the light ray was parallel to this edge, we can already figure out what the angle is, because it's a 45-degree angle prism. Therefore, the angle between the light ray and the normal line is 45 degrees. Again, this is only true if this light ray path is parallel to this edge. So we've got a normal line here, it's an angle of 45 degrees. Let's figure out how this light ray is going to travel when it goes into the glass. Now don't assume, oh, incident angle of 45 is greater than 42, it's going to totally internally reflect. No. This light ray is traveling from air to glass. So that means in this case, it's going to refract into the glass block and it's going to refract towards normal. Now how much the angle is, you can calculate it out, but for the sake of this video, we're just going to move on. So when it gets to this edge, it's not parallel to any sides. You'll find it's a non-zero angle, and at this point, again, it's going to refract when the light ray gets out into air, because this angle is not going to be greater than the critical angle. So when it goes out into air, it's going to refract away from normal, like so. And you can see that the emergent ray and the incident ray are not parallel or perpendicular to each other at all. So do not assume just because we're using the 45-degree angle prism that you're going to get that beautiful ray path of perpendicular rays. Now let's take a look at how the light ray would behave when it enters prisms of other angles. Let's start first with a prism that has an equilateral cross-section. That means that the angles are 60 degrees for each angle. So say we have a light ray coming in from the left like this. So because the angle is 60 degrees, so if the light ray path is parallel to this edge, we have the normal line at which the ray path enters the boundary, and based on the mathematical Z rule, we know that the angle between the ray path and the boundary is 60 degrees. But remember, whenever we want to measure the angle of incidence of the light ray, it is measured between the ray path and the normal line. That means that the incident angle is 30 degrees. So when the light ray enters the glass block, it's going to refract towards normal. And when it reaches the other side, here's a normal line, light rays moving from glass to air. So it's going to refract away from normal, like so. So again, the emergent ray and the incident ray are not parallel nor perpendicular to each other. What if we use a right angle prism, but the other two angles are not 45 degrees? So say we've got a prism like this, where the other angles are 30 degrees and 60 degrees respectively. Again, let's have the ray path entering the prism from the left side, like so. At this point, the light ray is perpendicular to the surface, meaning it's parallel to the normal line. Therefore, incident angle is 0 and the refracted angle is 0 degrees. The light is going to travel in a straight line until it reaches this angle H. So I've drawn a normal line here, which is 90 degrees to the surface where the light ray has reached the boundary. Putting triangular math into place to figure out the incident angle, we have a right angle triangle here. This angle is 30, therefore this angle is 60 degrees. At this point, the incident angle is between this light ray and this normal line, and that would be 30 degrees. We know the light ray is traveling from glass to air, but to figure out whether total internal reflection happens, we need to compare this angle to the critical angle. And as you can see, the angle of 30 degrees is less than 42 degrees, which means that total internal reflection will not occur. So the light ray is going to refract out into air, and it's going to refract away from normal like this. So the emergent ray and incident ray not parallel nor perpendicular to each other. Now, you might be wondering, oh, but couldn't the light ray enter from another phase so that it can undergo total internal reflection? You may be right. Let's take a look. So say now we rotate the prism and we have the light ray again entering from the left-hand side like this. At this entry point, same thing, light ray is going to travel in a straight path because incident angle is 0, therefore refracted angle is 0. So when it reaches this boundary where it's trying to exit out into air, here's a normal line, and now let's figure out the incident angle. So triangular math, we have the 90 degree angle here, 60 degrees, therefore this angle is 30 degrees, which means that for this point, the incident angle is 60 degrees. Let's check against the two conditions. First condition, the incident angle of 60 degrees, is it greater than the critical angle of 42? Yes, it is. Second condition, light ray is trying to travel from glass to air. Higher to lower optical density? Yes, which means that total internal reflection will occur. But here's the thing, for total internal reflection, it still obeys the law of reflection, where the incident angle and reflected angles are equal. So if the incident angle is 60 degrees, that means that the reflected angle will also be 60 degrees. You'll find that the ray path does not travel straight down. In fact, it travels this way, where the total angle between these two ray paths is 120 degrees. So when this light ray reaches the boundary, it's not parallel to the normal line. It's trying to exit the glass block at a non-zero incident angle. So what happens at this point? To visualize, here's the normal line, and the light ray is trying to move from glass into air, which means that very likely it's going to refract away from normal like this. So the emergent ray and the incident ray are not parallel nor perpendicular to each other. So yes, the angles of the prism which we use is very important when it comes to applying total internal reflection, so that the optical device that we are using will help us observe the objects correctly. By the way, here's a bonus meme because my slides are never complete without a meme. So where do bad rainbows go? They go to prism. It's a light sentence. It gives them time to reflect. So now that we've gotten our quota for lame laughs, let's move on with the lesson. Now, besides applying total internal reflection in devices, we can also observe total internal reflection in natural daily phenomena. So for example, if you were a fish, you can actually see other underwater creatures behind a rock because of total internal reflection. So if you were the fish, or maybe if you want to be the jellyfish, let's say we want to try to look at each other. The rock is in the way, so whatever love story you're supposed to have, it's not going to happen, right? Not necessarily, because total internal reflection can happen easily in water. So the light rays, instead of traveling straight, can actually reflect off the surface of the water due to total internal reflection, enabling these two underwater creatures to be able to see each other. So if you were a swimmer underwater, if you could actually look up, you can also see other objects behind a rock due to total internal reflection. Now, total internal reflection not only happens in glass or water, it can also happen in air. And a naturally occurring phenomenon of this is a mirage. Now, what is a mirage? So a mirage is like an optical illusion where we will perceive something to be on the ground when it's not really there. You hear a lot of stories about this in the deserts where people have reported seeing water on the ground, but when you get there, there's no water. In fact, the stories of the Flying Dutchman, go read up about it, is believed to be in mirages. So they're not actually ghost ships. It's just that there's a ship somewhere else properly sailing on water, but perceived to be floating and flying above the surface of the water. Now, a mirage can only happen on a very hot day. And why is this? So let's look at this diagram. We've got someone here in the desert and a cloud in the sky. So the mirage can only happen when the surface is very hot. That means it's got a low specific heat capacity, or it's a good heat conductor, so it tends to absorb heat. Some of you may even have observed mirages on a road. For example, if you're in a car on a very hot day and you're looking straight ahead, sometimes you can see what appears to be a puddle of water in front of you on the road, but when you get there, there's actually no water. So this also works because the surface of the road is very hot, very low specific heat capacity. So how does a mirage actually occur? Like I said, this only happens when the surface where we're observing the mirage on has a low specific heat capacity or tends to get hot very, very quickly. Because it gets hot so easily, it causes the air just above that surface to be very hot as well. And as we move further away from the hot surface, of course the temperature gets cooler. So to help you visualize this, I've put layers of different temperature air here. So red is representing very hot air, and as it goes up, the air is cooling down, so the cool air I've represented as blue. Now before we go into the light rays, some of you will be arguing, but wait a minute, doesn't hot air rise? We know that hot air has lower density and it should rise, which means that the cooler air should sink. And yes, you are right. But in this case, why is it the other way? It is because of the very hot surface. So imagine that this sand here is acting like a heater. It's very hot. It's continuously heating up the air above it. So when the hot air rises, it's moving further away from the hot surface, so it tends to cool down. So by the time it gets up, it's cool. It's trying to sink again. But when it sinks, it gets heated up by the heat source again, and so on and so forth. So guess that's convection current, but we're not here to talk about convection. If you want to know more, go watch my videos on convection. For now, let's just understand that in this case, although hot air is supposed to rise, and it does, the air above the sand is much hotter simply because it's continuously getting heated by the very hot ground. Now, in order to be able to observe objects, remember that the light ray must enter our eyes. So let's say we have a light ray reflected off the cloud and it's going to try to enter the observer's eyes. In hot air, the air particles are further apart from each other compared to colder air. Because the colder air particles are closer together, we'll find that light tends to travel more slowly in colder air and travels much more quickly in hotter air. So let's have a light ray coming from a point on the cloud, like so. Now before we move on, just to clarify about these layers of air, I've drawn the layers of air here just to help you visualize what's happening with the light rays. In reality, we don't have layers of air like this, like, oh, all this is one temperature, next is all one temperature. No, in reality, it is a gradient of decreasing temperature. But if I were to draw gradients, I can't draw the ray paths. So that's why in this case, I've used the layers here just to help you visualize what's happening between the different temperatures of air. So remember that in reality, this is not how it actually looks like in real life. It is actually a gradient of temperature. But for now, let's use these layers to help us understand. When light is traveling from the cloud towards the eye of the observer, light ray is traveling from cooler air to warmer air. That means that when it travels down, it encounters air that has a higher temperature than the layer of air before it. So because it's getting warmer, this means that the light ray is traveling faster. So the light ray is traveling faster, it's going to refract away from normal. So here's the normal line, and you can see I've drawn a light ray where it is refracted further away from normal compared to the incident ray. When this light ray reaches the next temperature gradient, again, it's going to refract away from normal. And this process keeps going until the angle of incidence is greater than the critical angle. So that means that at one point, you'll find that the light ray will undergo total internal reflection. So when the light ray enters the observer's eye at this point, the observer will see a cloud along this path. And obviously, the cloud is not going to be floating in the middle of the air. You're going to see the cloud formed on the surface of the ground like this. And because clouds are basically, water that's floating in the air, when we observe the cloud on the ground, it looks like water on the ground. That's why when mirages are observed in the desert or on the road, we tend to see puddles of water, because those puddles of water are actually the image of the clouds that we see on the ground like this. So that's how a mirage is formed. Now, besides light, sound can also undergo total internal reflection. Let's take a look at what happens in this situation, starting first with sound in daytime. Now let's say we've got these two young lovers who are trying to recreate the iconic scene from Say Anything. So we've got this young man who's got a boombox and he's trying to play the sound for his beautiful girlfriend to hear. Again, I'm going to put the different layers of the different temperatures of air to help us visualize what happens to the sound. Sound travels at different speeds in different temperatures. So for hotter air, because there's more energy, sound tends to travel faster compared to colder air where there's less energy. So when it's higher temperature, more energy, the air particles can move faster, therefore transferring sound more quickly. Compared to colder air, which is moving a lot slower, so the transfer of energy is also much slower. This time, the sound is coming from the bottom where the radio is. So I'm going to draw an arrow to represent the direction of the sound wave. So when the sound is traveling from the bottom layer to a higher layer, it's traveling from warmer to cooler air. So remember, sound travels faster in warmer air, slower in cooler air. That means the sound is going to be traveling more slowly. So when it travels slower, it's going to refract towards normal. This keeps happening at every layer. As you can see again, the sound is refracting towards normal, enabling the sound to easily reach his girlfriend who is on a higher floor. So yes, whatever love song he's playing for her, she's going to be able to hear it clearly. Now, of course, one thing we do know about sound is that it's omnidirectional. That means sound doesn't travel in one direction. It actually spreads out because sound is parabolic in shape. But basically, even if the sound was omnidirectional, let's say if I'm drawing sound waves like this, because sound waves tend to travel upwards, you'll find that the sound waves tend to curve upwards towards the listener. By the way, she'll be able to hear the sounds from the boombox clearly, and even if he's speaking, she may be able to hear him quite clearly. But if she were to respond, he probably can't hear her. Why? Because, as we can see in the daytime, sound tends to travel upwards. That means that if she were to speak, the sound of her voice will tend to travel upwards, away from him and not towards him. So if she says something, he's going to be like, "What? I can't hear you. What? Speak louder." Some of you may have even experienced this phenomenon where your friends might be on a higher floor and you're on the ground floor. So when you're speaking, they can hear you. But if they try to shout back, you'll be like, "Dude, I can't hear you. Can you speak louder?" So it's not that your friends are not speaking loud enough. It's because of physics. The sound tends to travel upwards in the daytime. Now, what about sound in the nighttime? So now let's say this guy decides to visit his girlfriend at night, again with his boombox. And in terms of the temperatures of air, finally, the balance of the temperature gradient is restored. As we have already learned, we know that hot air rises, and in this case, yes, the warm air will be on top, and the cooler air will be at the bottom. Why? Because at night, the ground is much cooler. It's not going to heat up the ground, so the hot air gets to stay on top. So in this case, when the sound is traveling from the boombox, it's going to be traveling through the cooler air first before reaching the warmer air. Let's start with one arrow to represent the sound wave. So sound is traveling from cooler to warmer air. And as we know, sound travels faster in warmer air, which means it's going to refract away from normal. And at this point, it could refract in such a way that the incident angle is greater than the critical angle, causing the sound to totally internally reflect. Now, some of you may say, "Hey, of course this is cheating. The angle here is already so big." So let's start with a smaller incident angle this time. You'll find that the sound wave is still going to refract away from normal because the temperature of the layer of air above it is warmer. And as it keeps going up, it's going to refract further away from normal until the incident angle is greater than the critical angle, causing the sound wave to undergo total internal reflection. And yes, we do know that sound is omnidirectional, but because of the way the sound waves are behaving, you're going to find that the sound wave ends up curving downwards. So it's going to be very difficult for the young lady to hear the music that her boyfriend is playing from this boombox. So if you ever want to recreate this iconic scene from the movie, Say Anything, if the person that you're targeting is on a higher floor, then you've got to do this in the daytime, not at night. So the comparison between these two situations of the sound in the daytime and sound at night explains a lot of real-life phenomena. For example, if you live in a high-rise, you'll tend to hear the sounds from traffic much more clearly in the daytime compared to at night. But at night, sometimes you still hear a lot of sound because at night, sound can travel a further distance due to total internal reflection. And now we've finally come to an end to this video about total internal reflection. If you'd like to know how to solve some questions or go through some worked examples with regards to total internal reflection, I'll put that in another video because I think this video has been long enough already for you to sit through. If you found this video to be educational and helpful, please click like, do comment about how this video has helped you, and of course subscribe for more free physics lessons. Do check out my YouTube channel for videos on other topics which you might find helpful. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Happy studying!